last time we were looking at an algorithm that actually computes the sign of X using a Taylor series. And we were actually looking at the nth Taylor polynomial. So that means it's a truncated series, and how we would actually solve this if we were to code this in MATLAB. So one thing that we know about numerical algorithms, okay? So a numerical algorithm is either stable or unstable. So what does it mean to be stable? So an algorithm is stable if small changes in the initial data produce small changes in the final result. Okay, so that's what it means to be stable. And if an algorithm is not stable, then it is unstable. Now, some algorithms are conditionally stable. So that means that they're stable only for certain parameters. Okay, so you'll know if your algorithm is stable or not, because if your algorithm is correct and it is coded, it's a correct algorithm and it's coded correctly, but when you're solving the problem, you're getting answers that are blowing up, then it's either unstable or you don't have the right parameters to make it conditional. It's conditionally stable and you don't have the right parameters. Okay, so I have one other definition. And so this one says, so here's our definition of linear and exponential growth. Okay, so suppose that E naught is the error introduced at some stage of the calculation. And then I'm going to call En is the error n iterations later, or n calculations later. Okay, so here's what we get. First definition is that if En is proportional to some constant times n times E naught, okay, then the growth in error is linear. And here C, some real number. And if En looks like a constant raised to the n power times E naught, then the growth in error is exponential. So we expect that as we have some error in our calculation at some particular time, that that error is going to move into the next calculation, and then that error moves into the next calculation. The problem is if that error is growing exponentially, then there's a problem. If that error is growing linearly, then that's pretty much what we consider stable. Okay, so we would have something that looks like this. So I don't know which calculation it is, but we're going to start with E naught. So here is E naught at some calculation. Okay. And then if the error, and I'm going to draw really thin, let's do a little gray line. So if the error at k plus 1 and then k plus 2, and then we keep going to k plus n, looks like this, then that is stable linear growth. But if it looks like this, I'm only drawing the gray line for my benefit to be able to just draw a curve. So if instead it looks like this, then this is unstable exponential growth. And rather than go through the examples in the book, I'm going to have you look at the two examples that are in the book for linear and exponential growth. Okay. So now I want to talk about rates of convergence. So I think we did, let me go back. I'm trying to keep my notes organized. Simple algorithms. And then now I should have put in here. Let me insert here. B stability. Okay. And then C is going to be rates of convergence. Okay, so we know by definition what it means for something to converge. Okay. So let's just think for a series for a moment. AN, and we're assuming that this thing converges to some number A. Okay, so we say the limit, we say that AN converges to A, that is the limit as n approaches infinity of AN is equal to A, and by definition, that means for all epsilon greater than 0, there exists a number n that's also positive, such that the absolute value of AN minus A is less than epsilon whenever little n is bigger than capital N. Okay, so that is the definition of convergence. And that's just a convergence of a basic sequence, okay? So we can also say that the absolute value of AN minus A is less than or equal to some, let me do there exists a K first. There exists a K greater than 0. Oh, okay, I need to write the whole thing. Trying not to write the whole thing, but I'm going to have to. All right. So definition. Suppose we have two sequences, beta n, which converges to 0. And alpha n, which converges to A. If there exists a K greater than 0, with the absolute value of AN minus A less than or equal to K times the absolute value of beta n, all right, for n large. Then an converges to A with an order of convergence that we're going to say is big O of beta n. Okay. So for example, when we use the Taylor series, so we want to use the Taylor series to approximate the derivative. Okay. So we have f of x plus h is equal to f of x plus f prime of x times h plus f double prime of x times h squared over 2 factorial plus dot dot dot. So if I take and I'm going to write f prime of x times h is equal to f at x plus h minus f of x minus f double prime of x times h squared over 2 factorial minus f triple prime at x times h cubed over 3 factorial minus dot dot dot. And when I divide by h, I get f prime of x looks like f at x plus h minus f at x. I'm going to divide that by h. That's our difference quotient minus f double prime of x times h over 2 factorial minus dot dot dot. So our error term is, this is our biggest term here. So we tend to take this here as our difference quotient. So we have f prime of x then is the limit as h approaches 0 of f at x plus h minus f at x all over h. And then this next term here is basically what we say on the order of h. In other words, it's relative to what h is. So if whatever I have in for h, that's what my error is going to look like. Okay, so my error looks like h. So if as h goes down by a half, my error should go down by a half. Okay. Where's that problem I wanted to do? Let's look at, so this says then, so now let's consider the limit as h approaches 0 of the sine of h over h. Okay, we know that if h goes to 0, we can compute that that limit is actually 1. But what's its convergence? What is its rate? Of convergence? Well, let's see. The sine of h is h minus h cubed over 3 factorial plus h to the 5th over 5 factorial. That's right. Okay, now I'm confused about something I wrote back here. Why was that? Oh, because that is wrong. Okay, nice to see that that is wrong. Okay, nice to see that that is wrong. So that's fine. We're going to fix that. This is wrong, guys. We're going to fix it. I just now see my mistake here. This is cosine. This is not right. This one, okay, so, oh boy, what a messed up video. Okay, so let's go back and fix this here. So cosine, sine is the odd values. This is cosine. All righty, so let's go back and fix this. All righty, and then this is cosine. And let's go back. Nobody looked at the video and found my error. And this is a 1, because when you put in 0, x to the 0 is 1. Okay, so that should have been like that. Okay. And so therefore, our sum should start off as okay, now I see. So, wow, excellent to find my mistake. Okay, so I need to set sum equal to 1. And then down here, this is sum plus. All righty, there we go. Okay. Cosine is the even one, sine is the odd one. So that computes the sine. So let me go back and make sure I don't have. Okay, now that's right. Okay, so I need to change this to cosine. All righty. Okay, now let's go back. Okay, so when I went to write this out, I immediately knew that I had made a mistake because I was getting odd powers. And I know that this is odd powers. And so that let me know that what I did yesterday or Tuesday was incorrect. Okay. So this is alternating series minus okay, so now by alternating series theory, all right, we know that the error in any approximation that we're looking at can be maximized by the magnitude of the next term. So now let's look at the sine of h over h. So that is 1 minus h squared over 3 factorial plus h to the 5th. I'm sorry, h to the 4th over 5 factorial minus h to the 6th over 7 factorial plus dot, dot, dot. Okay, so now the sine of h over h minus 1 is equal to negative h squared over 3 factorial plus dot, dot, dot. So the absolute value of the sine of h over h minus 1 is less than or equal to the absolute value of h squared over 3 factorial. And so now we can say that the sine of h over h converges to 1 with rate of convergence order of h squared. Okay. All right, so you will be read a little bit of the section. The section will also give you some more examples to help you with this topic. Okay.